Okay, welcome back everyone. In this segment, we're going to be looking at energy in simple harmonic motion, as well as some applications. And so it's very important to be able to analyze any system in terms of its energy. And so we're going to start to do that. We're also going to put the ideas of simple harmonic motion to use in a couple of different physical situations. So first of all, total mechanical energy is conserved, and going back to our example of a mass on a spring, the energy is going to simply oscillate back and forth between kinetic and potential. So at the two endpoints, when we are at positive A and negative A, we're going to have all potential, and that potential is going to be 1/2 kA squared. And because the object won't be moving, that's also the total energy E of the system. And then in the middle, when the spring is unstretched, all of the energy will be kinetic in the form of 1/2 mv squared. But this gives us a way to convert back and forth between energy. We have kinetic and potential, and we're always going to have some combination so that the total amount of energy in this brown bar is going to be a constant. You get the idea. Okay, so here's a couple things to think about with an energy diagram. The total energy is constant, and potential energy goes as 1/2 kx squared, so therefore the kinetic energy must be the constant value minus 1/2 kx squared. And as a matter of fact, we can determine the speed at any time using energy. 1/2 kA squared is equal to 1/2 mv squared plus 1/2 kx squared. Okay? This means that v squared is equal to k over m a squared minus k over m x squared. I've canceled out those 1/2s, and I've subtracted the kx squared to the other side and then divided by m. So this means that v as a function of x, not as a function of time, but as a function of x, is square root of k over m, which we recognize, times the square root of a squared minus x squared. And so we can see that this makes sense because when x is equal to a at the endpoints, the velocity is 0. Also, when x is equal to 0, when we're in the middle, then we get a velocity equal to a root k over m, which you might recognize as omega a, which we've previously identified as the maximum velocity. So let's go back to this same practice problem that we had before, and let's find the maximum and minimum velocities attained by the glider, the max and min accelerations, the velocity and acceleration when we're halfway, the total energy, potential, and kinetic energy at this position. Now this is a lot of numbers, so we're not going to put all the numbers into this, okay? But what we found in the previous example is if you go through the math, you find that the amplitude is 0.02 meters, and you find that omega is 20 radians per second. So this means that the max and min velocity is basically omega a. Okay? So that's going to be basically plus or minus 4 meters per second. The acceleration is going to be plus or minus omega squared times a, and that's going to be, let's see, 400 times 0.02, that's going to be plus or minus 40 meters per second. Did I do that right? 400, hold on, I can't math today. So it's 400 times 0.02 is going to be, okay, plus or minus 80 meters per second. Sorry about that. Okay. Okay, so it actually turns out that I can't do math at all. This is 0.4 and this is 8 meters per second squared. Okay, so now let's find the velocity when we're halfway to equilibrium. Okay, now halfway from initial position to equilibrium is going to look kind of like this, that x is going to be 0.0075. So we want half of this. So that means that v of x is going to be equal to omega times the square root of a squared minus x squared, using x as 0.0075. Okay, and we plug in all the numbers for this, and we get 0.371 meters per second. But now we have to think critically about this. When it's at 0.0075, which way is it moving? It's moving in the negative direction. Okay. Now, we also want to find the acceleration. And to get the acceleration, we recognize that a is equal to f over m. The other way I could do this is plug into my a of t equation, but I don't know the time right now. I would have to solve more to do that. But it's easier to just say that the force is kx, okay? And that's going to be omega squared times x, which is 3 meters per second squared. And now we also have to think critically about this, that if the block is to the right of the 0 point, it'll be a negative acceleration. Finally, we want to find the total energy, which will be 1/2 k a squared. I'm going to refrain from putting numbers in right now. The potential will be 1/2 k x squared, using this x right here. And the kinetic will be the total energy minus potential, which will be equal to 1/2 m v squared at that point. Okay. So I'm not going to plug in all the numbers, but I just wanted to show you how to get that set up. So here's a diagram that we can use for another practice problem. And so what's happening in the first diagram is that a chunk of putty is falling onto this mass m when it's in its equilibrium position. And in the second example, it's falling onto it when it's at a position a1. So what we want to do is we want to find the new amplitude and period of the motion, and then we want to do the same thing if the putty is dropped onto the block when it's at one end of the path. So let's just take the first one, and we're going to start off with conservation of momentum. Because it's moving with the speed of v1, it starts with momentum of m v1. Then little mass m is going to fall onto it, and we can find its new v1 as equal to m over little m plus big M times v1. We can then plug this into kinetic energy. The kinetic energy that it started with was just 1/2 m v1 squared, and the final kinetic that it's going to have is 1/2 little m plus big M times this v final, m over little m plus m v1 quantity squared. Okay, now this is going to reduce down to big M over little m plus m times 1/2 big M v1 squared. Now the reason that this worked is the 1/2 kind of went in here, and we had m squared over little m plus big M squared, and one of those canceled out with this guy here, and the other one came down here. Okay, now we notice that this 1/2 m v1 squared is k initial, so k final is this fraction times k initial. Okay, now we can also say that E1 is equal to 1/2 k A1 squared, and that E1 would be the total energy before the collision, And the new energy after the collision will be equal to 1/2 k A2 squared, which can be equated to this kinetic energy. And so ultimately what we end up with is that A2 is equal to A1 over root big M over little m plus big M. And from that, we can calculate the period as T2 equal to 2 pi root little m plus big M over K. So total mass over K. Now in part B, there's no change in the amplitude because it's already at maximum amplitude, okay? But the period will change to turn into 2 pi root little m plus big M over K, just like before. Okay, now one more thing to keep in mind is that if we oscillate vertically from a spring, we have a restoring force and simple harmonic motion, but we also have gravity. So let me give you an example, okay? Let's say that we have a spring and the spring extends upwards and there's a block here that's about to fall on it. So I'll call this the 0 point and we'll say that this block is at a height of h. Okay, so this distance here is h. Maybe that's better. Okay, now this is sort of diagram 1. Diagram 2 is when it first collides with the spring. And again, it's at height 0. Okay, so this is the collision between the spring and this object. And then picture 3 would be when everything has compressed and gotten to its sort of maximum compression here. And maybe I'll draw my spring going the same way to be consistent. But that's compressed now. And the 0 point is right here, and it has compressed a distance x below the 0 point. So then the question is, how far is x compared to h and everything else? So I'll give this a mass of m, a spring constant of k, and we could write that the energy at point 1 is equal to mgh, because the spring is unstretched. The energy at point 2 is just 1/2 mv squared, with whatever v this is about to hit with. But the energy at point 3 is 1/2 kx squared, because the spring is compressed, plus 1/2 mv squared, because it might still be moving downwards with the speed of v, minus mgx. So now it has a negative potential energy. And then what you can do is you can compare any of these situations to each other. Okay, so we'll do one simple example problem and then we'll move on. Okay, so the shock absorbers in an old car are worn out. When a 980 Newton person climbs in, the car sinks 2.8 centimeters. So that tells us that K is F over delta X. And we're going to model this as a single body on a single spring. So that's why we can do this. And we can get that K is 3.5 times 10 to the 4th newtons per meter. From this, we can get the period of oscillation is 2 pi root m over k. Now how did I get that? Well, I've memorized that omega is root k over m. You don't have to memorize that. You can go back to ma equals kx, and then m d squared x dt squared is equal to, well, there's a negative sign, negative kx. So if you just remember that k over m is omega squared, you can get to this point. And then you can start doing things like omega is equal to 2 pi f, which is equal to 2 pi over t. So t is 2 pi divided by this, so it's times m over k. All right, so that can get me the period, and that period turns out to be about 1.1 seconds. And so therefore the frequency is 1 over that, which is about 0.9 seconds. Okay, next time we're actually going to talk about angular simple harmonic motion, and well, actually we're going to talk about it very quickly. Okay, so angular simple harmonic motion, you don't see this too often, but this is where you have a restoring torque, not a restoring force, but a restoring torque. So this is F equals negative K delta X, but we have theta instead of X, and we have torque instead of F. Okay, now kappa here is the torsional constant of the spring, and basically kappa would be equal to torque divided by angle. Okay? Finally, you can imagine the vibration of molecules as also simple harmonic motion. And you might remember from our forces unit that F is equal to negative du dr. So if you have a point right here, you're going to have a force that actually points inwards, and if you're right here, you have a force that points inwards like this. Okay? So if you have time, I invite you to search for this PhET atomic interactions. It's a very important and interesting simulation that tells you about simple harmonic motion in molecules. Okay, so next time we're going to talk about the simple pendulum and the physical pendulum.